with the one and only question on the doubt sheet. Can we say something about the dimensionality of the tangent cone? Okay, everyone remembers what is the tangent cone? How do we arrive at it? We start. What is the starting point for arriving at tangent cone? First thing is starts with the F. Everyone's forgotten after eating nice mithai at home. Well, how do we start with this whole idea of okay? How do we arrive at a tangent? Priyanka, how do we start with a tangent? What is the first object you have to start with? Bolo na, feasible sequence. I start with a feasible sequence, right? Feasible sequence was defined as what? Limiting direction. Means I'm standing at a point in the feasible set and I'm watching a sequence approach me, and I take that vector and divide it by a scalar sequence whose only property is what? Its length tends to 0 as I approach the point, right? And I take that limit, I get a tangent. The limiting direction is the tangent. So I got one tangent. From one tangent, how do I arrive at a tangent cone? Collect all possible feasible points and therefore collect all possible tangents, right? So that's how I get my tangent cone. So that is revision about tangent cone. So the question is, can we say something about the dimensionality of the tangent cone? Okay, so in the example that we took, it is one dimensional. Remember, the tangent cone was a line parallel to the y-axis at the point minus 1 comma 0, I think, or minus root 2 comma 0. Is it always one dimension less than the feasible set of dimensions? So the set was two dimensional because I drew the half circle. So the feasible set consists of points in two dimensions, and we found this tangent cone to be one dimensional, which is a line. Is it always the case? Will it always be the case that the tangent cone will be one dimension less? Will it be one dimension less? Can it be even less than that? Right. So if you take just one or two constraints, we got what we got. But I can have multiple constraints in such a way that the feasible set is a point. Right. That is also possible. It will be a very silly problem to solve, because if there's only one point in the feasible set, there's nothing to optimize. That is the solution, right? So in general, the dimensionality is going to be less than the overall space in which we live, obviously, but we cannot say it will always be one less than the overall dimension. Okay. All right, so let's restart our discussion about the KKT conditions. Okay, so remember, just to again refresh your memory, what is the KKT condition or the FONC telling us? It's a test. It's a test that you subject a candidate point to. If the candidate point passes that test, then we say that to first order, we believe this to be a optimal point. Okay, that's the meaning of this test. So for doing this test, it's like when you show up for a blood test, you have to give blood, right? Without blood, there is no test. So you have to provide a point to the test to say, okay, evaluate it for this guy. That's how it will work. Okay, and we said that let's look at, instead of proving this in full generality, we will prove this theorem, give a sketch of this theorem. Okay, everyone remembers now what this, let's zoom in a little bit. Okay, right, these were the if then conditions for this theorem. If what? Obviously I am considering a point x star to be a local solution to this problem, f and c are continuously differentiable, and most importantly LICQ holds. These 3 points have to be satisfied for us to start the test. If some of these are not true, there is no sense in applying the then part of this theorem. It's not applicable, and this is again a classic mistake. You do not verify, for example, that LICQ holds, then you solve your the KKT implications, get some lambda and land up with a contradiction. That's because you did not verify the first part, right? So first 3 conditions have to be checked, then I can apply the then part of it. Then several things, all of them are kind of formalization of the intuition which you already had. Grad of the Lagrangian should be 0, etc., and the complementarity condition, right? And then we said, okay, let's look at a toy problem. Toy problem was objective function which is linear along with two inequality constraints. The feasible set was the pink shaded region, okay, and then we said, okay, let's take some point in the feasible set. What all will be the implications of this theorem? Can we say that f and c's are continuously differentiable? Yes, right. What is the second point that I have to verify? That is the third point. Second, I thought that was the third. Okay, for x star to be a local minima, okay, and the third is LICQ. Do you think LICQ will hold? It will hold because grad C1 will be what? 2x1, oh sorry, minus 2x1 minus 2x2, and grad C2 will be what? 0 comma 1, right? So for most points this should be linearly independent. We can verify it in particular for specific points, okay. So for any point x star inside this feasible region, these are the tests that we have to subject this point to, okay. The first one is very trivial, obviously it should be feasible. So I say C1x and C2x both should be greater than or equal to 0. If that is not true, there is no conversation, okay. Then we come to the various possibilities. Possibilities are simply whether the equalities are strict, I mean whether the inequalities are active or not active. That's how we will separate these two things. Why? Just so that we understand clearly how to approach the proof, okay. And so you have these four possibilities, either of them are 0, one of them is 0, the other is 0, neither are 0. That is how we are going to split this. So turns out that if you look at 2a, right, so if you look at 2a, that is the case where the Lagrangian has the most complicated expression. Will you agree? Case A, the Lagrangian has grad f minus lambda 1 grad C1 minus lambda 2 grad C2. So this is like the most general possible thing that you can think of, because I have three vectors to worry about: grad f, grad C1, grad C2, and they all have to sort of work in harmony to get this expression. The simplest would be D. Only what does D remind you of? It reminds us of an unconstrained optimization problem, right? So why? Because the inequalities are inactive. A very simple way to understand or visualize this: supposing I give you a problem, minimize x square plus y square such that x square plus y square less than 1. What is that? What is the feasible set? X square plus y square less than 1 is the constraint. What does that look like? Interior of a circle, and I'm asking you to minimize x square plus y square. Where is the solution? Origin. Is the inequality active there? No, right? We're not on the, it's clearly inside. So here is a point where the Lagrangian is basically just grad f. You could have started at some interior point, done gradient descent and arrived at the solution. So that's basically what D is telling us. So D in some sense is the simplest. B and C are similar, that there's another grad C1, but A has grad C1, grad C2. Okay. So now let's look at how to handle this with our toy example in mind. Okay. So for A, what do we need to show? We need to show that that grad x Lagrangian of x lambda, this was equal to 0, which in turn implies that grad f is equal to lambda 1 grad, let's put x over here, right. Any other conditions that the KKT conditions tell us must hold true? Look at your A, B, C, D, E. Is there anything else I have to tell you? Or rather, is there anything else that the KKT theorem tells us? Little louder. Lambda should be greater than or equal to 0 because this is an inequality constraint. Because this is an inequality constraint, constraint, I have to say that the Lagrange multipliers have to be greater than or equal to 0, right? So this is both. So if you look at your KKT theorem, this is what this is what must hold true. All right. Now let's we will keep flipping between algebra and geometry. This is clearly the meaning of grad L equal to 0, right? That's what algebra is telling us. Now I want to draw your attention to the right hand side of this thing. Okay, think of lambda 1, lambda 2 as non-negative variables. Okay, think of grad C1 and grad C2 as fixed vectors. Let's just say why, because x is fixed. I'm evaluating this whole thing at a point x. What kind of geometric object does the right hand side remind you of? Something, yes, of course it's a linear combination. Can we get something more specific than that? It's also a convex combination. Can I get something even more specific than that? Parallelogram, yes, okay. There is another, parallelogram is correct. But in terms of what we have recently been reading about, what else could you say? Hint is ice cream. It's a cone, not tangent. It's a cone. This object is a cone. This the lambda 1 and lambda 2 being strictly greater than 0. This is what is going to give us a cone. So let's define. So what I'm saying is grad f should actually live in a particular cone. And what is the cone being specified by? Grad C1 and grad C2. What was, you can verify, last class we had defined what was the definition of a cone. If a vector lives in a cone, then its positive scalar multiple should also live in the cone. Right? You can verify that the definition will easily hold true over here. So let's now nicely define this cone. Let's before we proceed further, let's just draw this. Okay, here is my point x. Okay, this is in the feasible set, and just for definiteness, let me draw at this point x grad C1 points here, grad C2 points here. Could be any two directions. I've just picked it arbitrarily. Okay. Okay, so which way is my cone? Where is my cone? Upside, right? It is this top half region over here. So if I were to sketch it over here, it's basically, right? The way to quickly check it is, supposing I do lambda 1 equal to lambda 2 equal to 1, where will I be pointing? I will just be joining the parallelogram and coming to that point. That point has to belong to this. Now put lambda 1 equal to 0, put lambda 2 equal to 0, I'll get the two ends of it. To get the other side, I have to put actually negative, which is not allowed. So the cone is defined like this. This is a way to quickly sketch it in your mind, right? So we are saying that grad f should belong to this cone. Okay, let's just sketch the feasible directions here. Does anyone remember how we define the feasible directions given grad C1, grad C2? What do I start with? So I need grad C1, then orthogonal to, no, linearized feasible directions. What are the directions in which I can go to first order so that I still stay in the stay feasible? What was it? Wasn't it grad C1 transpose D? What should I say? Write this as greater than equal to 0, and grad C2 transpose D greater than equal to 0. If this was a equality instead of inequality, what would change? This would become equal, but in this case. Okay, so grad C1 transpose D greater than equal to 0 defines what kind of geometric object? half space, right? So I would draw something like this. And am I to the left or the right of this? I'm to the right of this. Similarly, I take grad C2 transpose D greater than 0, also a half space, right? So I sketch one thing like this, right? So what are my, where are my legitimate feasible directions? They're in this intersection over here. Okay. Anyway, this was just to give us some clarity on which would be a correct direction to go to. This is linearized feasible direction. After that, I would also have to consider what else? When I think of an algorithm, this has given me a set of regions where if I go, I will continue to be feasible. What is the other thing that I have to worry about? Not length. This has no mention of what? The objective function, right? It's grad C1, grad C2 who are dictating this. What is the other thing I'll have to worry about? Descent direction. Is this a descent direction? These two things together will help me to go forward in any algorithm, but we are not talking about an algorithm right now. Okay. So we are going to use one of the oldest tricks in the book to prove this, which is proof by contradiction. Okay. So okay. So proof by contradiction means I will assume that what? Grad f is not in this cone. Okay. So I need to prove this. So where can I draw my grad f? Anywhere but inside the cone, right? So I'm going to draw a grad f like this. Okay, grad f is not in the cone, so I've taken some arbitrary point over here. Okay. Now I'm going to do an interesting thing. I'm going to ask you first in words and then we'll write it mathematically. What is the point? So this is A. What is the point in the set A, the cone A, which is nearest to grad f? How would I draw this or figure it out? I'd drop a orthogonal onto this, right? So it would be something like this, right? This point I'm going to use a lot. I'm going to call this guy S. Okay, S is as close to grad f as A can get. That's the meaning of this guy. Okay. Now that you've gotten it by geometry, let's try to write it in fancy language. So S, is S the solution to an optimization problem? If I write it, if I think of it a little bit formally, is S the solution to a small little optimization problem? Yes, right? So it is, what is the variable that I'm allowing? From what am I allowed to choose to come up with this S? Any point in A, okay? So W belongs to A. What do I want to minimize? The distance to what? Grad f. So what should I write over here? Norm of W minus grad f, right? So this is a very simple example of a projection operation. It looks fancy when you write it, but it's just going step by step from left to right. I come up with this. Okay. So this is, it looks a little arbitrary that I started with grad f, suddenly I've proposed this projection point, but there's a reason I'm doing this. The claim is, if I look at this new vector S minus grad f, okay, S minus grad f which way will S minus grad f point? It will point from grad f towards S, right? So if I draw it, this is what the vector looks like. And you can check it very quickly, right? If I take the red arrow, which is grad f, plus the blue arrow, which is S minus grad f, what should I be left with? S, which is what I get, right? Because S is this vector. So the claim is that this S minus grad f is a very interesting vector because, well, you'll see it is both a feasible direction and a descent direction. We will show this. Okay, we will show this using simple geometry, that this new funny object that we have created from grad f, we got the projection point, and then I got this difference vector S minus grad f. This is both feasible and descent direction. So while the problem is still fresh in your mind, what are we trying to prove? We said that for the implication of KKT to hold, I should have that grad f must live in this cone. Then we said, let's do proof by contradiction. That means grad f should not be in this cone. Now, okay, that's what we started out with. Now, if I find that S minus grad f is both feasible and a descent direction, what does that imply? Why? So in your, this is why paying attention to every line of the theorem pays off. What is the first line of the if condition of the theorem? X should be a solution to, I mean, it should be a local minima of the optimization point. That is what I started with. Only then the then implications follow. Is that somehow being violated? Right? It is being violated because I have found a direction in which if I go, not only do I continue to be feasible, but I also descend, means improve the f. That means x is not a local minima. Therefore, the rest of the theorem doesn't hold. Therefore, f, the contradiction is there. Therefore, f must belong to the cone. Right? So there are several nested levels of logic happening here. Right? So if you are confused, we can revise it once again. Is there anyone who would like me to go over this once more? Okay. So what is the first statement of the if? X must be a local minima. That means in the neighborhood of x there is no better x. Then I said, okay, let's go proof by contradiction. Let us assume that grad f does not live in the cone. Okay, that cone came from the KKT theorem. Now grad f does not live in the cone, fine. So then we have constructed one new something, and I'm claiming, which I will prove shortly, that this new vector S minus grad f is both feasible as well as a descent direction. That means standing at x, I can improve myself in terms of objective function value. That is my contradiction. Therefore, what I started is wrong. Therefore, grad f will live in the cone. So that's the general direction that I want to go into. Okay. Yeah. So let's just make a note over here. If this is true, then x is not a local minimum of the problem, since f can be reduced further. Okay. That's the general. I want to give you the entire story that we are going to do before we get into the nitty-gritty details. Okay. So there are two claims. So there are going to be two sets of reasoning for it. Okay. So let's take the first one. Okay. Again, it pays. I'm going to use some properties of convex sets without proof, but they are very intuitive properties. Okay. The first property, S, the existence of S comes only once you give me grad f. Agreed? Once you give me grad f, I do a projection operation and I arrive at S. What can you say about the norm of grad f and the norm of S? Norm is a scalar. Can I compare scalars? Yes. Can you think of an intuitive relation between the norm of grad f and the norm of S? The length, the projection should have a smaller length in general than the original point. Okay, and remember I'm saying convex sets. You can have funny things happen with non-convex sets. Okay, so I can say that norm of grad f, okay, let's just, norm of S is less than or equal to norm of grad f, since A is convex and S is the projection of what, grad f. Okay, so everyone agrees with this. Okay, so from here I can do a little bit of tricks. I can, if I multiply norm grad f on both sides, it's a positive number, the inequality will stay as it is, right? So I can also write this as grad f, grad s, grad f squared. Okay, grad f square is also what? Grad f transpose grad f. Okay, the left hand side, is it, can I further reduce it by multiplying some cosine angle, some cosine of something? So I can say that grad f cos theta is less than grad f, agreed? Cos theta is less than equal to 1, so this is fine. Now what theta, this sounds like some funny exercise I am doing, just multiplying numbers on the left, on the right, but can I choose this cos theta to be the, can I choose theta to be the angle between grad f and S? Up to me. So if I choose it, what does the left hand side become? Grad f transpose S, right? So this becomes, or I can write this as S transpose grad f, and this becomes what? Grad f transpose grad f, right? So can I combine this now? I can take grad f common. What will I be left with? S minus grad f transpose grad f is what? Less than equal to 0. What does that imply? Actually, just I want to make one tiny correction. My starting point was assuming that grad f is not strictly not in the cone. So this inequality, should it be this way or should it be strict? Should be strict, right? So we'll just make one small correction over here, right? This is fine and this is what I get. Okay. And we all know what this is. This implies that S minus grad f is a descent direction. That was quite easy to prove, right? So the first part of the puzzle we have solved, we have found this S minus grad f is a descent direction, okay? But as you know, just proving descent direction is not enough, because it has to also be what? Feasible. It has to make sure that I stay in that set. Everyone clear with this argument?